Today's video is made possible by Brilliant.org.
Today I've got a really nice infinite matrix product. And what's really cool about this is it seems really daunting, but using an application of a recent video, we'll see that it collapses very quickly. So let's see what we've got. We'd like to find the product as n goes from 1 to infinity of these 2 by 2 matrices of the form n over 2 times 2n plus 1, 3 over 2n, 0, 1. So those are upper triangular matrices. And it's super helpful that those are upper triangular matrices because that will make us or give us the ability to find a closed form of the partial product pretty easily. That being said, let's maybe start to build the partial product in a somewhat general sense. So let's set AN equal to the following matrix. It's not going to be this matrix. It'll be a more general version of this matrix where we have little a sub n here, little b sub n here, 0, 1. So notice our matrix is most definitely of this form. So if we can get an idea for the partial product of matrices like this, then we're good to go to unravel this probably fairly easily, if you will. Okay, so now let's look at a couple of partial products. So the first partial product, well, that's just clearly the very first matrix. So red row-wise, we have A1, B1, 0, 1. Now let's look at the second partial product. So that'll be A1 times A2. I guess here we're making the decision that we're putting all of the new pieces of the product to the right. That's an important decision to make because matrix multiplication is not commutative. Okay, so let's see what this is. We have A1, B1, 0, 1, A2, B2, 0, 1. So now let's do that multiplication. And so by the standard rules for matrix multiplication, oh, and by the way, I did a video a while ago about why matrix multiplication is defined the way that it is. So if you're interested to see that, maybe check that video out. There should be a card up in the upper right of the screen right now if you want to check that video out. Do it after watching this video. So we'll take this first row, swivel it into this first column, giving us overlapping A1 and A2 and B1 and 0. And then do the multiplication and the addition. So this will give us A1, A2. Okay. And then what do we get for that upper right term? So we'll have A1 times B2 plus B1. So A1 times B2 plus B1 using the same method. And then for the bottom row, we have 0, 1. That's pretty clear. Now let's see what we have for A1, A2, A3. So I'll use the form for A1, A2 that we've already figured out. So we've got that, which we can just bring down. And then A3 will be the matrix A3, B3, 0, 1. And then using our standard rule for matrix multiplication again, that'll give us this form that is fairly easy to generalize, I think. So in this upper left term, we'll have A1, A2, A3. And then in this upper right term, we'll have A1, A2 times B3. And then next, we'll have plus A1, B2 plus B1. And then for the bottom row, we'll just have 0, 1. So I think we can maybe make some sort of general claim of what's going on over here. And and then we'll prove this general claim by induction. So if AN is equal to the matrix up there, so AN, BN, 0, 1, then the product as little n goes from 1 to capital N of our matrix AN has the following form. So I think this lower row is pretty clearly just going to stay 0 and 1. And then this upper left term is going to be the partial product of the lowercase a terms. So I could write that as the product as n goes from 1 to capital N of the numbers AN. And then what's going on with that upper right term? Well, let's notice that it's a sum, and it's a sum of the b terms where we multiply in a product of a terms depending on where we are. So here we have b1, and then plus b2 times a1, plus b3 times a1 times a2. So how could we maybe write that down most easily? Well, I think maybe this is the way. We have the sum as n goes from 1 to capital N of the product a1, a2, ending at an minus 1, and then bn. So something like that. Now I think that makes sense because the third term in this sum, if we read it from right to left, has a b3 and an a1 and an a2, and then descending down we see that this works out. Okay, so now let's prove this claim, and then we'll use this claim to get a closed form for our goal product.
Hey there, before we continue, I'd like to tell everyone about today's sponsor, Brilliant.org. While watching my videos is always appreciated, you get more out of learning by doing, and that's why I highly recommend you sharpen your skills with Brilliant. Brilliant's enormous library of learning content allows active learners like you to explore a variety of topics and skill levels, and Brilliant will support you at every step of the way. You'll be able to master whole topics gradually in as little as 15 minutes a day and learn anywhere, anytime, on your phone, tablet, or computer. Brilliant makes learning more like a game, with fun features that let you challenge yourself and compete with others. I recently used their resources to augment my Calculus 2 course, and I use it with my son who is in pre-algebra. See what I mean? No matter what skill level you're at, Brilliant can help you improve. But we're scientists here, so don't take my word for it. You should test it for yourself. Treat yourself to a unique hands-on experience by going to brilliant.org/Michael Penn, and the first 200 people will get 20% off their annual subscription. Thanks once again to Brilliant for sponsoring today's video.
So we'll use the principle of mathematical induction to prove this statement right here, this little subclaim. So our base case, well, that's already done during exploration. That would be the case where we take the product from n to 1 to 1. Or maybe 1 to 2 if you want to see a little bit more structure, but 1 to 1 is suitable for a base case. Now I'd like to point out that if you're presenting something on the board and you've done some exploration in front of your audience, then it's okay to say that this is done during exploration. That being said, if you're writing this up as a homework type exercise, all of that exploration is scratch work, and you'll actually want to write out the base case. So I always tell my students there's like an important difference between working through a problem with a class where you show all of the details and writing up a homework assignment. Now let's do an induction step, which starts with the induction hypothesis. So let's suppose for some k bigger than or equal to 1, maybe let's illustrate this is for some k bigger than or equal to 1, not for all k bigger than or equal to 1. We have, well, the statement holds. So that means this holds where capital N is equal to k. So I'll write that down. We have the product as little n goes from 1 to k of a sub n is equal to, well, this matrix where in the upper left we have the product as little n goes from 1 to k of a sub n, and then we have the sum as n goes from 1 to k of our product a1 up to an minus 1, and then bn, and then 0, 1. Great. But then after making the induction hypothesis, we consider the next case. So in this case, that would be the k plus first case. So I've got my product as n goes from 1 to k plus 1 of a sub n. But notice that's equal to the product as n goes from 1 to k of a sub n times a sub k plus 1. Now I can apply my induction hypothesis, and that'll give me the product as n goes from 1 to k of little a sub n for this term. Here I'm rewriting this using my induction hypothesis, and then I'm just going to bring this down. So my sum is n goes from 1 to k of the product a1 up to an minus 1 bn, and then 0, 1 in that lower. And then I multiply this by the k plus first matrix. So this will be AK plus 1, BK plus 1, 0, and 1. But now let's do our matrix product, and we'll see that we'll be essentially home free here. This is going to give us the product as n goes from 1 up to k of a sub n, all times a sub k plus 1. And then here we'll get the product a1 up to ak times bk plus 1 plus this sum. So the sum is n goes from 1 to k of a1 up to an minus 1 times bn, and then we have 0, 1 in my lower entry. But now I can put this AK plus 1 term into this product, and I've got exactly what we need. That'll turn to the product to K plus 1. So let's do that. So I can put a plus 1 there, and that's just multiplying that in, so we don't need it anymore. Then I can do the same kind of thing over here. I can introduce this into this sum, and that just adds something on the end. But that's the exact formula I need for this k plus first term to finish this proof by induction. Okay, so now we're good to go, and we'll apply this claim to our, setup. Okay, so I've opened a little portal up to rewrite our goal product as a limit of partial products. Now we're going to apply our claim to take that partial product into just a single matrix. So let's see what we're dealing with now. So this will be equal to the limit as capital N goes to infinity. Now let's focus on this upper left term, which will be the product of these terms right here from our matrix. So notice, let's do it with the numerator and the denominator separately. So the n equals 1 term in the numerator is 1, the n equals 2 term in the numerator is 2, the n equals 3 term is 3, all the way ending at capital N. So we have this product 1 times 2 times 3 up to capital N, but there's a name for that, and that is capital N factorial. Then we've got a bunch of copies of 2 as well. Well, 1 for each of these, so that'll be 2 to the power n. And then finally, we've got a rising product of odd numbers. So the first one will give us a 3, the second one will give us a 5, so we've got 3 times 5 times 7, ending at 2n plus 1 in the denominator. That ends up giving us 2n plus 1 double factorial, where we've defined that in previous videos. That's like a relative of the factorial. Okay, so that's that upper left entry. And then notice that the upper right entry is fairly similar. This is a product of the first n minus 1 terms, and then we're multiplying that into bn. So using pretty similar methods, we can write this as the sum as n goes from 1 to capital N of n minus 1 factorial over 2 to the n minus 1 times 2n minus 1 double factorial times 3 over 2n. And then our lower entries are just 0 and 1. And now we're going to bring this limit into each of these terms of the matrix. And for this, I'm going to leave you with a little bit of a homework exercise, and that's to show that the limit of this upper left term is in fact 0. So I think this isn't too hard to check. Maybe if you have a nice trick to do it, post it in the comments. And then bringing this limit into the second term, we'll turn that finite sum into an infinite sum. So we'll have something like this. 0 goes here, and then here we'll have the sum as n goes from 1 to infinity. Maybe I'll bring that 3 outside, and then I'll have n minus 1 factorial in the denominator. I'll have 2 to the n in the denominator. Sorry, that n minus 1 factorial should be in the numerator. The 2 to the n comes from the fact that we built that 2 up with this 2 right here. And then we have 2 to the n minus 1 double factorial times n. And then 0, 0. And then in that previous video that I said this was connected to, we found a closed form for this. But before we found a closed form, we actually showed that it could be written in the following kind of more aesthetic version. So the sum as n goes from 1 to infinity of 1 over n squared times something called the central binomial coefficient, which is 2n choose n. and then I've got a 0 and a 1 here. Sorry, that should have been a 1 over here. And this is this nice format for this sum. That being said, we also found a closed form for that, and then 1 multiplied by 3, that was equal to pi squared over 6. And that gives us our final value here for this matrix. It's 0, pi squared over 6, 0, 1. So I think that's a pretty nice result. So, and that being said, I think this maybe uncovers another interesting fact, and that is we took the product, or the infinite product, of matrices, all of which were invertible, and we ended up with a matrix that's not invertible. So not only did we get this nice like infinite product of a matrix that's related to essentially the Riemann zeta function evaluated at 2, but we found an example of an infinite product of invertible matrices which is non-invertible, and that's a good place to stop.
Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.